And today's talk is about HTTP headers. I have two tips for any aspiring speakers in the audience. Number one is don't spill coffee on yourself before you're going to deliver a talk at a conference. And secondly, wear dark clothing in case you spill coffee on yourself before you give a talk at a conference. I'm happy to say I'm 1 for 2 on those this morning. So let's talk about HTTP. 1997 saw the standardization of HTTP 1.1, which is the version that most of us have been using for the last 20 years. And it looks a bit like this. Built into an HTTP exchange is metadata, both on the request and on the response. And it's pretty simple. In HTTP 1.1, we got the concept of the host header. And this was really important because for the first time, we were able to host more than one website per IP address. And in the response, there are only a few things that are really important. One is the content type, so we know what kind of data we're going to be receiving. And one is the content length, so we know how much data we're going to be getting. So today, that response looks a bit more like this. And hopefully, some of these headers are things that are new to you that you don't recognize, because we're going to be talking about quite a few of these today. I'm interested in this for a couple of reasons. One is that I used to be an elected member of the W3C Technical Architecture Group. This is a group of 9 people who are like a guidance body for the architecture of the World Wide Web. And we review specifications and standards proposals that standards bodies have that they want to incorporate into the web platform. And I thought that this would be JavaScript APIs and new HTML elements. But a surprising amount of the time, they were HTTP headers. So these were some of the headers that we reviewed whilst I was on the tag. The other reason is that around this time last year, I was at a W3C conference in California. And Steve Souders, who is a well-known performance guru and author of various books on web performance, cornered me and we had breakfast in this restaurant. And he said, "Andrew, I wrote this blog post a few years ago about invalidating scripts in the browser cache. So I want to serve a long-lived script like an analytics script or a style sheet or something. And I want my end users to not continuously hammer my server for this object because it's pretty static, it's not changing. But I want to be able to update that script without changing the URL and then have every browser immediately request a new version." And he came up with this hack to do this. Uses location.reload and various kind of iframes and things, and it's pretty ugly. And he said this was a few years ago, there must be a better way of doing this now. So I said, well, surely, Steve, you must have heard of the clear site data HTTP response header. You just attach this header to any HTTP response from your origin, include the word cache, and blows away everything in the end user's cache that's associated with your origin. And he said, "No, I've never heard of that. It's amazing." And I thought, wow, if Steve Souders has never heard of this, we probably haven't done a good enough job of talking about these new headers. I should write a blog post. So I wrote a blog post. And I looked at all of the different techniques there were for clearing the browser cache, including the one that Steve pioneered and also various others that I came up with, and the use of the clear site data header. And in doing so, I realized that it's actually not supported by any browser. Which was a bit unfortunate. It is fortunately now supported by Chrome, and I believe it's also coming very soon in Firefox. But I thought, well, what is the state of the art for all the other headers? You know, what about all the other things that we standardized a year ago or 2 years ago or 3 years ago? What's the uptake like? How are people adopting these things? And also headers that have kind of come and gone and we shouldn't be using anymore. Are they still hanging around? So HTTP Archive is a project sponsored by Fastly and Google and various other people. It takes the top 1 million websites and runs them through web page tests every 2 weeks. That generates about 50 million HTTP requests. And the full HTTP request and response exchange is then put into a BigQuery database, and anyone can then query that database for anything they want. It's a really nice snapshot of what the web looks like today, and it's updated every 2 weeks. So I wrote some SQL to look at those 50 million responses. So that's some in the region of 300 or 400 million HTTP response headers, and started to analyze them, started to rank, what headers are the most popular response headers that we see in the HTTP archive. And start to divide these into various categories, like headers that are best practices, that we should be using more, or we should be using better, or maybe are already being used in a really good way. And also headers that we should be seeing a lot less of, or which are not used correctly or are misunderstood. So let's start with those, the headers that we don't want. And the first header in this list that I didn't recognize, one of the most popular headers, it was in the top 20, P3P. Who knows what P3P is? Show of hands? Yeah, not very many people. Well done for those who do. It's emitted by about 10% of websites in HTTP archive. And most curiously, it's quite often set to the phrase, "This is not a P3P policy," which makes you think, is it a P3P policy or is it not a P3P policy? And the backstory here is that it's a standard that was created in order to give websites an ability to declare a kind of machine-readable privacy policy. And the idea would be that user agents would surface this information to the end user in a way that was consistent across all the websites that you visit. So you can set your privacy preferences, and your user agent would be able to alert you in an automated way if the website was not compatible with those. This seems like a really good idea, right? It seems like today this would be a great way for us to comply with some of our GDPR responsibilities and so on. Unfortunately, this was kind of ahead of its time. It was standardized in 2002. It was only ever implemented by Internet Explorer. And interestingly, Microsoft implemented it in such a way that it gated access to a small piece of browser functionality that people wanted to use. Now, because the value was never surfaced in the UI anywhere, it didn't actually matter what you set the value to. It wasn't validated. So this is not a P3P policy. It would pass that check. Needless to say, please don't use this header. It's a bit of internet trivia, and it's kind of indicative of the messy way in which the web evolves. So to go from that, which is pretty niche, to something which probably everyone in the room is familiar with, the expires header. One of the most popular headers in the database, present on almost 80% of HTTP responses. The expires header sets a date at which the content should be considered stale in cache. This is pretty simple. It's interoperable. It's supported pretty consistently by all browsers. The question in my mind, though, is why is it always Thursday, the 1st of December, 1994, at 4 p.m. GMT? Overwhelmingly, this is the most popular value by a very, very long way. Why? Anybody can hazard a guess? There's no default value for an HTTP header, but it is the example in the spec. Why would you copy and paste the example from the spec? So I have a couple of theories about this. One is that almost uniquely for a standardized date format, the HTTP date format includes the day of the week. So if you think of some arbitrary date in the past in your head, in order to form an HTTP date, you need to know what day of the week that was. And you just often can't do that. If I think of like 1st of January 2000, for example, I don't know what day of the week that was, so I can't do that easily. The second thing is that it seems like people feel like a date that's just a little bit in the past is not in the past enough. So commonly, these dates are a very long time ago. So they're in the early 90s, before HTTP was even standardized. So, FYI, a date that's 2 hours ago is fine. It's just as in the past as a date that's 20 years ago. And if you do copy the example from the spec, which is also fine, you should see this next to it, which says, if a response includes a cache control field with a max age directive, a recipient must ignore the expires field. There's a little bit of spec language here, but by field we mean header, and by recipient we mean browser. So if you include a cache control header in your response, then you don't also need an expires header. That's what it's telling you. So it's impossible to ignore this. Look, it's right there. It's right underneath the example that you copied and pasted from the spec. So it seems very unlikely that anyone would include both of these headers in the same response, except obviously 64% do. So that's a lot of wasted bytes of expires headers which are being overridden by a cache control header that's part of the same response. So by all means, use expires as an indicator of freshness, but you do not need to use an expires header and a cache control header in the same response. And quite commonly, I see this kind of thing. Now, the person who wrote this is really, really insistent that this response not be cached. So much so that we have an expires header in the past using the correct date. We have a cache control header listing every single possible cache control directive, including some that are not standards. And we have a pragma header, which is not actually a response header at all. Pragma was standardized as a request header. So if you want something to not be cached, this is absolutely fine, unless you're dealing with some kind of really crazy HTTP client that really doesn't understand HTTP properly. Now let's move on to another header, XCache. And this header is kind of a representative of a large number of headers which don't exist. There's no link on this slide to a spec because there is no spec. There is no document. There's nothing that tells anyone what this header is. And yet, it's on 13% of the responses in HTTP archive. That's quite curious. Also, it's curious that everybody seems to agree on what it is because it's almost always set to the word hit. And admittedly, this is our fault, or at least it's largely the CDN industry's fault, because when responses come through, CDNs like Fastly, we will add debug headers like XCache to tell our customers whether these responses were served from our cache or whether we had to fetch the resource from their upstream servers. And we really probably shouldn't be doing this. It's in good company. There are over 1 million headers in HTTP archive, which don't mean anything. They are not interpreted by the browser. They're not used in any way for end users. Unless you have some kind of browser extension that is specifically looking for one of these headers, it is not doing anything to change your internet experience. So these are just a waste of bytes on the wire. And of course, 99.99+% of people consuming your web content are not your own development team. So in the case where some of these headers are useful for debugging purposes, you could write some code like this on your edge network or on your edge router, or like whatever is the sort of frontmost part of your architecture to strip off headers which are not functional. Now, another one that I used to use myself before I did this research was XFrame Options. The purpose of this header is simply to prevent your site being included in another site in an iframe. Why would you want to do this? Well, it's possible to make an iframe completely transparent. And so the practice of doing this, loading a foreign site into an iframe, making it transparent, and then convincing a user somehow to click on a specific spot on that page is known as clickjacking. And this used to be very popular for people to generate Facebook likes and that kind of thing. So using this header, we can prevent our site being framed by another site. It's extremely popular. It works pretty well, and it's pretty simple. The only thing wrong with it is just there's a slightly better way of doing it. And I discovered there's a content security policy directive called Frame Ancestors. And this allows us to control more precisely how and whether our site can be framed by another origin. The benefits to this are, number one, you already have a content security policy, so it's one fewer headers. And secondly, content security policy is a better spec. It's better written, it has better interoperability, so you can expect a more consistent behavior in edge cases than you would with XFrame Options. And finally, let's mention via. Now, via is uniquely amongst the headers I've talked about so far, both a request and a response header. And it is added by intermediaries through which your request or response passes. So imagine you have Fastly or some other CDN, or you have your own caching layer in front of your microservices architecture at the back end, or maybe your end user is in a university or an institution that's funneling all its outbound web traffic through a proxy. All of these situations will result in a via header being added to the request. And then when the response comes back from the server, a via header will be added to the response as it passes back through those same layers. Now, the via request header is actually very important because each of these layers is essentially terminating an HTTP request and they making a new one to the next layer in the chain. So we need to make sure that all of these layers speak the same version of HTTP, and that's the first job of the via header. The second job is to prevent loops. So let's imagine you have two CDNs, and they are both configured to treat the other one as their backend. So if they don't have a mechanism for detecting that they've already seen this request before, and in fact they have it kind of as a live connection, then in theory they could continually connect to each other until they ran out of sockets. So the via header prevents this by telling you that a request has already gone through you, so you can refuse to forward it again. But the response header is informational. This is just a header that's added on a way back down the chain, and ultimately it tells the browser which proxies process this response. It doesn't do anything with that information, so it becomes a little bit like an XCache header, which you don't really need. So now we've done some cleanup, let's talk about best practices. What should our HTTP responses look like? And the first and most important thing I need to talk to you about is content security policy. I was a bit glib earlier when I said obviously you've already got a content security policy because statistically the likelihood is that you don't. Although I'm sure in this room the statistics are more than 3%. But that's pretty bad. And the reason for this is I think that a content security policy is hard. It's hard to implement. The average length of policies that I saw in the archive was 600 bytes. It's one of the longest headers that you commonly see. Conceptually, it's very simple. You just provide a list of origins that your page is permitted to make connections to in order to load resources. You can subdivide this by types of resources. You can say these origins for script, these origins for images, and so on, or you can just have one set of origins for all kinds of resource loads. This creates a kind of a firewall in the browser. So you load the page, which is the first arrow at the top, and then once you've got the page, you then have an execution environment that is subject to essentially a firewall defined by your content security policy. This means that if you have some vulnerability that allows an attacker to execute scripts on your page, there's a limited amount of stuff they can do with it. They couldn't, for example, load a larger payload to further attack the page, and they couldn't exfiltrate data from the page to their own origin. And of course, there may be other ways they can do this, but this is one defense against that. The problem is things like this. So this is a small part of the largest content security policy that I found in HTTP Archive. It's 10K. This is prefixed to every single response this server is generating. And it includes some really awesome little nuggets, like it includes unsafe inline, which allows any script to be executed within the response body of the HTML itself. It includes unsafe eval, so we can construct scripts dynamically and eval them within the page. It includes domains like cloudfront.net, which anyone can serve content on. Includes Tag Manager. Anyone can sign up for a Tag Manager account and upload scripts which are served on that hostname. And my personal favorite is its whitelisting style.amazonaws.com. So you may as well write, x debug : and then 10K of underscores before every response, and it would be as effective as this content security policy. So by all means, use content security policy. In fact, definitely use content security policy, but think about it in terms of the security benefits that you're getting from it, not what you have to write in it in order to do what you want to do. Because you will end up with a CSP that's essentially offering you no protection at all. So another security header that's very important is strict transport security. How many times do you think people go to your website and type https:// and then your domain name? Basically, no one ever does that. And yet, hopefully, your site is not available over HTTP. You're only serving on HTTPS. So there are a lot of occasions when somebody will hit your site on unencrypted HTTP, and you'll redirect them to the HTTPS version. So the purpose of this header is simply to prevent that from happening. As soon as an end user sees this header on any response from your origin, any future connection to your site, even if it appears that the user wants to connect over HTTP, will be made over HTTPS anyway. And the browser will then present the URL to the user as HTTPS without having to do a redirect. This is actually a very aggressive header. You can use it with the preload directive, and that will enable browsers to socialize that information to all other instances of the browser. So in theory, one single Chrome user coming across your strict transport security header will then make every single other user of the Chrome browser connect to your site only over TLS. So it can be extremely aggressive. It can also be pretty devastating if your TLS is not set up correctly. But if it is, and once you're happy, then adding include subdomains and preload to this header will offer you a lot of security. Now, moving from security to privacy, the referral policy header is another thing that depresses me because it's really not adopted as widely as I think it should be. And I think this one is particularly interesting in light of the fact that we're all under a lot of pressure to comply with regulatory requirements around user privacy. But those regulatory requirements tend to distract us, and they tend to be around the specific things that are subject to regulation, and not the things that maybe are of equal concern to end users, but just aren't subject to specific rules. So referral policy prevents the exfiltration of data that is contained within URLs. So if you link from your page to some third party, and that link sits on a page that has a query string that contains some kind of user inputted information, then that information will be included in the request to the third party when the user clicks the link. So let's say I'm on your search page. I've searched for something. My search query will potentially be leaked to the site that you're linking to. So referral policy is a way of limiting the amount of information that is shared. My preference is the origin when CrossOrigin option, which allows the full URL to be included in the referrer header when linking within your origin, and it will just include the bare origin when linking to a foreign origin. Now, there's a whole suite of response headers that start with access control. These are part of a feature called CrossOrigin Resource Sharing, or CORS. These headers, unlike the others that I've mentioned so far, are permissive headers, so adding them to your site makes your site less secure rather than more secure. The most secure way of deploying CORS is not to deploy it at all. But of course, being able to interact with foreign origins is sometimes very useful, so it is a useful feature that is popularly used. One of the most important things about CORS is that it makes responses specific not to the server emitting the response, but to the origin of the page making the request. So if I request a resource from a page that was served by origin.a.example.com to, well, let's say requesting origin.example.com, as it says in the slide, to foreignorigin.com, then foreignorigin.com needs to generate a response that cites the name of the origin making the request. That means it's very difficult for us to cache that response and serve it to anyone that wants it. In fact, in theory, we could serve completely different responses to different origins that were making the request, which kind of makes you feel a bit uncomfortable about this as a part of web architecture, because it means that the URL is no longer solely the only piece of address information for a piece of content. In fact, this has been something that was very controversial while I was on the tag, particularly around the idea of credentials. So one of the things that you choose when you're making a cross-origin request from a page is whether to send credentials, i.e., do you want to send the cookies that are associated with the origin you're sending the request to? If you choose to do this, then the server that you're sending the cookies to has to acknowledge that it needed them by replying with an access control allow credentials true response header. If it doesn't do that, or it sets that header value to false, then the browser will not let you see the response that you've received, even if the response is a valid response. And also, it will look like a network error rather than telling you exactly what the error was. So you just have to guess and resubmit the request without credentials, or the other way around. So I don't know what the solution to this problem is, but it's quite an interesting indication that headers start to become not just metadata, but part of the identity of the object itself. If you're interested in just getting a very quick health check on the state of your site's headers. Securityheaders.io is a pretty good place to go for this. It will give you a basic kind of grade and advice on how to improve your site's headers. Nothing to do with me or Fastly, but I find it quite a useful tool. Mozilla also have a tool called Observatory, which essentially does the same thing. Either one of those is a good place to go to start. Now let's go from security and privacy to performance. Who here has heard of client hints? So client hints is a mechanism for requesting that the browser send you additional information about the user's environment, about their device, and about their browser, and potentially about their personal preferences. And we can request this using this XCache header. Now, the currently standardized client hints include the device pixel ratio of the primary display, or the display on which the browser is currently in focus, the width of the screen, and the width of the viewport. And also a Boolean telling you whether the user has enabled data saving mode in their browser. We can also send a lifetime header that tells the browser how long we want to receive that information for without having to continually re-request it. So on subsequent requests, after we've emitted these headers, the browser will then send us the information we've asked for, the width of the screen, the viewport width, the device pixel ratio, and whether the saved data is enabled. And this client hints is designed as a framework. So many other of these client hints might be added in the future to give us additional context for what kind of device and what kind of environment the user is operating in. The problem that I have with client hints is they're not sent in the first request. You have to ask for them, and as a server, you're not in a position to make a request to the client. You can only send it information in a response. So when the browser makes that first request for the page, you don't get any client hints. You can ask for the client hints in the response, and then you will get those client hints for all of the sub-resource requests that are made from that page. So you'll get the client hints for the images, the scripts, the style sheets, the fonts, and everything. But you can't use that information when you're generating the HTML page itself. So I'm worried that this will be an incentive for developers to make that first response a redirect back to the same URL with an XFrame header, so that we then get a request with the client hints, especially for things like save data, because in theory, setting save data to 1 could prompt you to completely change the HTML that you send the user. Like CNN, for example, has a very, very big default response, but they also have CNN Lite, which is a very, very much smaller payload. There are many new client hints that are being proposed. This is a proposal from Mike West at Google to rethink the user agent header, which is probably a good idea. So instead of the browser identifying itself as Mozilla, followed by a string containing the names of almost all of its competitors, you will have a series of headers that divide the user agent into a number of discrete tokens. So, for example, the UA will just be the primary identifier for that browser in the major version, platform architecture engine. Also, things like accept language. I think we've concluded over time that accept language is too complicated to format. There's too much fragmentation within the ways that browsers format an accept language string. There are too many different ways of coming up to of forming essentially the same accept language result. So a client hint could make accept language far more cacheable. Would creating a new mechanism for browsers to identify themselves just essentially lead us to the same problem again? Like browsers will just lie in the new mechanism, and then we'll create another new mechanism that will try and prevent them lying again. I don't know, but I think the reset button is overdue, and pushing the reset button on user agent is probably a good idea. Now the link header was standardized with HTTP. It's a very, very old header. And it was designed to provide semantic relations between resources. So you can be looking at a resource, say a chapter of a book, and the link headers can give you relations to other resources like the previous chapter, the next chapter, the index, that kind of thing. Now, we don't really use the web like that anymore, but the link header is still generically useful for linking together resources that are semantically related. And the most popular use of this header today is preload, which is to say, this other resource is going to be needed in order to render this page, so please load it as soon as possible. You do it like this. It's commonly used for fonts because fonts can be discovered very late in the process of loading a document. You need to scan the page, discover the style sheets, load the style sheet, then discover the font declaration. So you still possibly don't load the font at that point because you need to know whether the font is being used somewhere on the page. So fonts can actually be kicked off very late in the waterfall. If you want them to be loaded a lot earlier, then link preload is a good way of doing that. This is from a case study by Adi Osmani at Google that shows how adding link preload affects the Tinder website. And you can see that we start with some of their JavaScript loading at around the 1 second mark. And I'm talking there about when we start to load the JavaScript, not when it's finished. After we add the preload tags, all the JavaScript starts to load at the same time, around the 200 millisecond mark. So we can substantially increase the speed at which we get to a usable interactive site by using preload. The problem is that we have to wait until the server sends us a status code before we can send headers. So preload substantially improves the performance. We can start to load our fonts a lot earlier, but we still can't load them as early as we'd like to. And here's an illustration of why. So when I type in a web address and press enter, the first thing the browser does is it makes DNS lookup for that host name. Then it negotiates a TCP plus TLS connection. Then it sends the request. Then it waits for the server to think. And the server is going to be doing some database access, some authentication, templating, maybe reaching out to some other microservices, assembling a response. And ultimately, the server will decide this is a 404, or this is a 200, or whatever the correct HTTP response code is. And then once it's decided that, it can then emit a header block. And then it can start streaming the response, which it might still be building. So we already support the idea of streaming responses, but we have to wait for that status line before we can start to do that. So at Fastly, we're working on a new spec, which we call early hints. This will be a new HTTP status code. And the description of this status code is basically, don't know yet. So you would emit this status code very quickly after receiving the request, before you've done any server-side processing, and it would give you the opportunity to send some headers. And most notably, it would give you the opportunity to send link preload headers. Then the browser can start loading those critical resources before we've decided whether this is going to be a 200 or not. So now the waterfall can look like this. We can start loading those critical resources whilst the server is still considering the original request, and we haven't yet received the first bytes of the response. Now, also within performance, we have measurement-related headers. Any performance engineer will tell you that sort of 50% of the challenge of performance is measurement. And one of the best additions to the platform in this area has been the server timing header. So server timing allows us to start exposing some of what's going on during that server think time, which we're addressing with the early hints status code. We can start to try to reduce the amount of server think time by understanding where we are spending that time. Are we spending it in the database? Are we spending it in Memcache? Are we spending that in HTTP requests to other servers? This is the syntax. It's quite flexible. You can attach a millisecond timestamp to a label, or you can just emit a label, or you can emit a label and a description. In Chrome, this data actually gets rendered as part of the timing panel of DevTools. It's the only browser currently to visualize server timing. And it's pretty rudimentary. One of the limitations of server timing is that there's no order information. So you can see that although we have a waterfall in the main data here, for server timing data, it's all just stacked up on the right. And that's because there's no information within server timing that tells us that this happened before this, or this blocks that. Part of the reason for this is that server timing is expected to be generated across multiple pieces of physical infrastructure with different clocks. So it would be an ineffective solution to include timestamps. We could add some kind of mechanism for saying this before that, or this blocks that, or something like that, and hopefully that will be in a later revision of this spec. What's really interesting to me about server timing is that it has a JavaScript API. So within the page, we can actually get access to the data that we're sending, and then you can beacon that data back to some collection server or aggregation server. And actually, this is one of the first instances where we have a JavaScript API into the data that we're receiving in our HTTP response headers. Most of the time, within the page, within the JavaScript we run on the page, we can't really see the data that is in the HTTP header section. Really, the only other instance is cookies, but cookies have side effects. They have a client-side state. So what if we were to use this to just send arbitrary data to the browser? This is really useful for a lot of reasons. One reason is that many large sites will generate relatively static pages and then save them in an edge cache or some kind of cache that is very hot and close to the end user for performance. But they want to enhance these pages with a little bit of extra data which personalizes them. Something like the number of pages left on your paywall credit, for example. So imagine that you could add headers to the response to add that extra information, and then you could use JavaScript to reassemble it. Now, I'm not saying this is a good idea. It's definitely a misuse of the header. But it's interesting that this is currently the only header that would actually let you do this. I want to finish with mentioning a couple of headers which don't really exist in a usable form yet. Feature policy is shipped in Chrome. In fact, Chrome is kind of racing ahead of the rest of the web on this. One of the problems that we have with a web that is now 30 years old is that it's big. The platform is huge. And so the attack surface is huge. The range of APIs you can inadvertently trigger is huge. And some of the features that it exposes are really powerful. So wouldn't it be great if we could selectively turn off bits of the web platform that we know we're not going to use? Either because we just want to avoid any potential vulnerabilities that might exist in those APIs, or because we want to self-police. We know that we have a large development team, and we don't want anyone to use a feature that we've decided we don't want to use. Let's say, for example, you've decided as a matter of policy that your website will not autoplay video on page load. That's something you'd have to police with code reviews and so on, or you could write a feature policy that just says autoplay none. So now the ability to autoplay a video does not exist on the web within this page. This is really powerful. I love this feature. And it's a framework like Client Hints, so we can add more and more policies as the best practice, or what we consider to be best practice on the web, evolves. As of today, there are 10 reasonably well-agreed policies, which are listed on the left here, and you'll see these if you go to MDN and search for feature policy. But like I said, Chrome is kind of racing ahead, and if you actually go into Chrome Canary, enable experimental web features, and query for the allowed features, they actually shipped quite a lot of additional features which have not yet really been discussed in great detail in the standards community. But some of these are great ideas, like document write, for example. So if you set document write none, then document.write doesn't exist as an API on your page. That's for you and also for any third parties you load into the page. And I recall in a previous job, we had all sorts of trouble trying to get advertisers to stop using document.write as a mechanism to add their content to the page. This would be a very simple way of solving that problem instantly. So I'm very excited about this. I'm less excited about the fact that this is going to turn into a bit of a content security policy problem. This is currently the tightest feature policy you could set. And as more and more policies are added, this would just get longer. So hopefully at some point there will be some consolidation, and you'll be able to reference a policy like, best practice web 2019 or something, and that will aggregate quite a lot of these policies together. The Google AMP team have specifically highlighted feature policy as one of the things that they need in order to move AMP from being a proprietary solution to one that's standards-based. And the final thing is origin policy. And I'm a bit sad about origin policy. It's been proposed for over a year and just doesn't seem to be getting very much interest. But the idea of origin policy is to take this situation where we had this really clean response, and this became this really long and messy response, to take this and get back to that simple response again. Because if you think about all the headers that we've talked about today, very few of them actually relate to the specific response we're about to receive. So something like strict transport security, for example, is manifestly an origin level setting, because it doesn't matter which response I attach it to, it will apply from then on to my entire origin. Some things are theoretically response-specific, like content security policy or referral policy, but in practice, no one really has a different content security policy for every page. They have one for their whole site. So it makes sense to take a lot of this stuff and move it out of individual HTTP responses and into something which maybe we might call an origin policy. And it could be a JSON file that we store at a well-known location and just reference in every HTTP response. So we can separate the stuff which is common across all responses from the stuff which is specific to this response. Now, the reality is this doesn't actually improve performance very much, if at all. Because with HTTP 2, we now have header compression. And the header compression dictionary is connection level. So when we make a second response, if we include the same headers that we included on the first response, then the size will be basically 0, because the connection already has a compression dictionary that contains that content. So it's not going to improve performance very much, but it does improve developer experience, because you're able to segregate the headers which are origin-specific from those which are response-specific. So I've covered a lot of headers today. This is kind of a little cheat sheet for to take home and think about. The top left ones are ones that, apart from feature policy, are ones which, if you don't have them already, you probably should. There are very few use cases that don't call for CSP or strict transport security or referral policy or link preload. At the same time, in the bottom right, if you're still serving any of these headers, maybe think about whether you really still need those. If you want more detail on any of this, or indeed more headers, because I really have only covered a very few of them, then this blog post is a good place to start. This is the ones that I would like to see less of, and there's a link at the bottom of this to a part 2 where we cover the good ones. And you can get the slides from my SlideShare account. And that's it. Thank you. Do we have, I guess, if you have questions, feel free to come and talk to me.